Welcome students to the first online lecture of the semester. So let's just get right into it. This is lab 9. The topic is Faraday's law. Faraday's law is given by Faraday's law. Can you see this? Yeah. Faraday's law is given by V equals dVt of phi, where V is induced voltage and phi is flux. So Faraday's law tells us that a time-changing flux produces an EMF, or an electromotive force. So this is known as electromagnetic induction. So electromagnetic induction is the fundamental operating principles of transformers, which converts power at a fixed frequency from one voltage to another, inductor coils, which we will get to in future labs, electrical motors, generators, which convert mechanical energy to electrical energy, and solenoids. Okay, so today we will experiment with solenoids. So this comprises a conductive wire coiled into a cylindrical shape. Wire coiled cylindrically. So before we look at the solenoid, let's remember last time we looked at a current carrying wire. This wire with current I, right? And we said that we can use the right-hand rule to figure out which direction the magnetic field is pointing. So if we point our thumb in the direction of the current, our fingers curl around the wire and give us the direction of the magnetic field. This. And the magnetic field is given by V equals mu naught I over 2 pi r, where I is the current through the wire, and R is the distance from the wire to any arbitrary point. Okay. So if we change the geometry of the wire, we change the geometry of the magnetic field. So just pretend we're taking the same wire and we're wrapping it around like this. Into a kind of a coil. So you can imagine that the current is still pointing along the direction of the wire. So we're going this way, up, down, okay? And so at every point along this wire, we have the magnetic field curling around. It's on that side it goes opposite way. Oops. Okay, it's kind of confusing, but you get what I'm going for. Okay, so we can look at a cross-section of the solenoid, and we can construct the net magnetic field of the entire solenoid, which is just a superposition of the smaller magnetic fields like these. So side view is like this. So this is a cross-cut or cross-section of the solenoid, where these circles represent the wires. So on the top we have the wires coming out of the board, and on the bottom we have the wires going into the board. Kind of like this, a half cylindrical shell. Okay, make sense? You can't answer me anymore. Alright, so then let's apply the right-hand rule to these wires. So at the top, the current is coming out of the board. So the magnetic field wraps counterclockwise. Counterclockwise, counterclockwise, and again counterclockwise. comes into the board. And so the magnetic field points clockwise. Clockwise again. Get the picture. Clockwise. Alright. So the point here is that these individual magnetic loops will superpose or sum to add to the solenoid's magnetic field. So let's draw this again down here. So we have these wires going out the board on the top, into the board on the bottom. And then, as you can see here in the middle, the arrows all point to the right. And so they sum to something that looks like this. Right, and then the top and bottom, they also sum in the same direction. Right. We get something that looks like that for the solenoid. Alright. So this is our solenoid magnetic field geometry, and unlike the wire, the magnetic field is given by mu naught I over L. So mu naught is the magnetic permeability, I is the current, L is the length of the solenoid, and N over here is the number of turns, or number of times that the wire wraps around the cylinder. Okay, so this is the magnetic field of the solenoid. So now let's talk about flux, another important concept for this lab. So flux is given by phi, which equals V times A, where V is the magnetic field and A is the area. So remember, flux was in Faraday's law, so V equals negative V phi dt. So the induced voltage is equal to the negative time change of the flux. So flux is the magnetic field times the area. And it describes the integral, or the total, of the field density passing through some given area. So the flux is interested in this area. So it's V times A. Stronger magnetic field means stronger flux. Larger area means larger flux. Alright, so I think that's all the theory you need for this lab. So let's get into the experiment. Alright, space here. Alright, so part one, we'll be modeling the changing flux as a function of height. So modeling changing flux as a function of height. So we have V equals negative D phi Z dt. So phi is a function of Z, or height. Z. So what we'll be doing in part one, or what I will be doing in part one, is giving you the data, so confusingly, is dropping a magnet through a known distance. So we have a magnet that's falling over some known height h, and then it will pass through an inductor coil. So we'll have a solenoid, actually. The magnet will fall through the solenoid, and this changing flux of the magnet falling through the solenoid, will induce a voltage on the solenoid, which we will measure with the oscilloscope. Okay, so the voltage is proportional to d phi dt on the sine. We can say cleverly that d phi, or this expression is equal to d phi dz times dz dt. So we just introduce an extra dz into the equation. It's all the same. And then dz dt is just the velocity in the z direction. And then we're left with d phi dz as our coefficient. So notice that the velocity is proportional to the voltage. So what we expect if we change the height that we drop the magnet through is we should see a graph of voltage versus velocity that's essentially the goal for part 1 of the lab, is to illustrate the proportionality between the induced voltage and the velocity of the bottom magnet. Okay, so from classical mechanics, we get the velocity of the magnet by applying the conservation of energy. So potential energy is going to be equal to kinetic energy. Right? So I'll leave that as an exercise for your lab report. So what you should end up with is the velocity is equal to square root of 2gh. So you'll know the gravitational constant, you'll know the height, and so you can calculate the velocity. Right, so for part 2, we will find the induced voltage on a secondary solenoid. Due to a changing flux caused by a primary solenoid. So you have one solenoid that will have a signal being input to it. So the voltage on the primary solenoid will have some time dependence. And then we will have a secondary solenoid inserted into the first. And the time-changing flux in the first solenoid will induce a voltage on the second solenoid. So just by virtue of being in the vicinity of the first solenoid's magnetic field, we should see a voltage on the second solenoid. Alright. So let's write Faraday's law again. So the voltage on 2 is equal to negative time change of the flux from the first solenoid. So V2 is equal to negative v dt of phi 1. So we can write phi 1 as a sine function, because that's the signal that we're getting from the power supply, is an AC signal. So phi 1 max is the amplitude times sine omega t, where omega is 2 pi f, just angular regular frequency. Okay. So there is this side. So then to find the voltage induced in the second solenoid, we just take the time derivative of this expression. So phi max is independent of time, so it comes outside the derivative. The time derivative of sine omega t is just omega cosine t. I do that. Is there a negative sign there? I don't think so. Alright, so there was a negative sign. So V2 equals negative phi 1 max times omega times cosine omega t. So that's what the function looks like after we've taken the time derivative. Okay. So we're only interested in this coefficient here, which is the amplitude of your wave. So V2 max is equal to the absolute value of omega, which is the driving angular frequency, and phi 1 max, which is the flux from the first solenoid. So this is the voltage that we expect to see, or the maximum voltage. So for part 2, we will perform an error analysis. On my measured values of V2 max theoretical versus V2 max experimental. So there's a few more calculations to look at, because you need to calculate the flux of the first solenoid. So again, flux is given by V times A. And actually this time we have to multiply it by n to account for each turn of the loop. So phi 1 max equals v max primary times a times n, where n is just the cross-sectional area, or the overlapping area. And v, again, is just the magnetic field of the primary solenoid, which again is given by mu naught I primary times n primary over L. So knowing the number of turns on the first solenoid and its length, and the current moving through that solenoid and the magnetic permeability, we can calculate the magnetic field on the first solenoid. We can use that to calculate the flux, knowing the area and the number of turns on the second solenoid. And then once we have the flux, we can multiply it by the driving angular frequency. And that essentially gives us the max voltage or the amplitude on the voltage of the second solenoid. So I think that's it. For now, we'll walk over and record the experiment for your reading pleasure. Yes. All right. How long was that?
That was 15 minutes.